So far, we've discussed how neural networks or a single hidden layer neural network can approximate any given function. What function are we trying to approximate when we do classification? It's essentially a function that divides the feature space into two different regions, right? So let's say we've got these red examples and then we have got these blue examples that you can see on your screen. So these ones, let's say they belong to two different classes, and the function we are looking for during classification is essentially this function, the green function that you see, that is able to divide this or partition this feature space into two parts. And that has been a recurring theme throughout our discussion on machine learning. These methods, what they do is they partition the feature space into meaningful ways that are useful to us for classification, for regression, for other type of problems, right? If you think of each neural network making a localized, or each neuron in a neural network, or a single hidden layer neural network, to make a single straight cut, or localized single straight cut, then this function, this green function, can be thought of as a summation of, or a weighted summation of all of these cuts. So we have got a cut here that essentially targets this particular region, and then we have this particular cut that targets this region, and so on. And then we can have a weighted summation of all of these cuts that gives us an approximation of this green function. That is the impact of universal approximation on, or shape approximation using neural networks on practical problems such as classification. The question is, how many cuts do we need to get an arbitrary approximation or an arbitrary good approximation of this given green function? Now, we've done that earlier as well, so I'm not going to repeat that experiment. You can watch a video where we made a number of cuts, but this time we're interested in how many cuts are needed. Now, our previous discussion essentially says that as the complexity of the curve grows, the number of neurons grows, or the number of neurons required to approximate that grows exponentially. And that can be a very big problem. So how do we reduce the number of cuts? Now, we can reduce the number of cuts by exploiting symmetries in this feature space. If you're a physicist fan, think symmetries. It's the exact same thing of symmetry. Let's say this function, for example, is symmetric with respect to this point over here. Then what we can do is perhaps fold this feature space, and then that is going to reduce the number of cuts that are needed exponentially. So that is the idea behind kernel functions. What do kernel functions do? They change the distance between 2 points, essentially achieving a fold of the feature space. Neural networks do the same thing. They have the same effect of folding this, but they do it in a different way. What they do, what these neural networks do, is they learn a transformation, or what deeper neural networks do is they learn a transformation that changes this data representation or makes a fold of this feature space, and then that reduces the number of neurons required for approximating that shape. Let me walk you through an example. Let's say, before we talk about the mathematics, so let's say we've got a figure over here. Let's say if you fold it along this particular line, along the dotted line that you see in this plot over here, sorry, this one over here, then the number of required cuts is going to be halved. And if we exploit this property, or if we make a fold along this particular dotted line, then we can get even a smaller number of folds or number of cuts that is needed. And if you can fold it again, then that reduce it by a factor of 2 at least. So the number of cuts that I need decreases every time I make a fold, and it decreases exponentially. That's really nice. And this is what deep neural networks do. What deep networks do is that they transform, they use more than one layer. So if I say we have a single hidden layer of neurons, this is the layer that is going to be, which feeds into the output layer. We know this bit is a universal approximator, but the number of neurons required for approximating any shape will be very large. So what we do is we add a layer that folds or transforms the points in this space in a meaningful manner. So we add another layer of neurons. So we take a two-dimensional input. Let's say we can have 3 neurons over here. And then what those 3 neurons do is that they transform this two-dimensional example into a three-dimensional example, which then feeds into this bit, with the hopes that once we train this whole thing, the number of parameters required for achieving a certain degree of accuracy or approximating this green curve is going to go down. So although we are adding neurons, but we are adding them in layers. And when we add neurons in layers, this can be thought of as a transformation from x to say a phi of x, which is being learned. And then that allows us to reduce the number of cuts that are needed. And you may want to revisit the video on a fold and cut theorem in order to understand this better, or this example better. But the main idea is that if we have a neuron with two hidden layers, neural network with two hidden layers, such that the number of neurons in the first, in the input representation is d, and then those are mapped to d dash. So this is the number of neurons in your hidden layer, in the first hidden layer. Then a number of neurons, the total number of parameters that you have is essentially this much. Okay, so that's the total number of learnable parameters. But to achieve a certain degree of accuracy, the total number of parameters can actually be smaller than what we had with a single hidden layer, and we can test that using the code that we have. There's a lot of text on this slide, and I welcome you to go through all of those papers that I've cited over here. But the theme of all of this discussion is deeper representations are more efficient to achieve higher levels of accuracy, or to approximate a given function with a higher accuracy in terms of the number of parameters, so that we are going to need fewer parameters to achieve the same degree of accuracy of approximating any given function. So and it's not just going to be fewer by a scalar factor. It's going to be exponentially slower, exponentially fewer parameters, or is this going to be exponentially more powerful in representing a given function? And you can talk. There are different proofs for that. I'm not going to go into those proofs. All that you need to understand here is that we are folding this. Each layer that we add achieves a transformation or a fold of the space. Okay, and because that changes the definition of the distance function, right? If we have 2 points A and B, right? If we have these 2 points, point over here, sorry, A that has a particular feature representation, and this has there's a point B. Once we use a hidden layer to transform this point A to phi of A, and the same transformation onto this B, the distance between A and B, as we measure it using this thing, let's say a Euclidean distance between these two, and the distance between phi of A and phi of B may not be the same anymore. So what we've achieved is essentially a fold of the space. And once we achieve the fold of the space, number of cuts required goes exponentially down. That is the advantage we get when we add more neurons in our hidden layer. And you can go through these papers, which essentially prove that a deeper representation is more efficient in terms of the number of required parameters, or the learnable parameters or weights of the neural network. Okay, so it has been shown experimentally as well. For example, this particular paper shows that, or this particular plot shows that the test accuracy increases as we go deeper into a neural network for a given task. So the number of parameters actually is lower than you would have if you had a single hidden layer neuron as well. Okay, so this is a proof that deep models are actually more efficient. And this is a simple proof of R using R code. You have an approximator, but this time instead of having a single layer, you have multiple layers in your neural network. So let's say if you've got 63 neurons in a hidden layer to achieve a curve like this, which is a pretty good approximator for this given function, we can achieve actually a better approximation using 7 neurons but in 2 hidden layers. So that's going to be a total of 14 neurons, but we have a smaller number of weights in comparison to this. So what this shows is that deeper networks are able to approximate a given function better, but at the same time they can be very difficult to optimize. And one of the reasons for that is this beast that we had talked about earlier. Once you have multiple neurons, multiple layers in your neuron, you can end up with these product terms of derivatives that can lead to vanishing and exploding gradients. So your optimization can be difficult even though your representation power improves. But if we can somehow overcome this challenge, or if we can optimize our neural networks, deeper neural networks, we can do a whole lot more, right? So coming back to the representation, evaluation, and optimization framework for multi-layer perceptrons, instead of having a single layer like we have over here, you can have multiple layers of neurons so that the output of one feeds into the next one. The evaluation bit is pretty much the same. And then you have optimization, in which you can use different type of optimizers, and then those are going to learn your parameters. The goal of all of this discussion is to help you understand why deeper networks are more efficient, or why these deep networks are in fashion, because they give us more representation power. Thank you.